Now that we have a little bit of hand on how the logarithmic expression and function works, we're going to talk about the graph of this and go through how to possibly pull out important pieces of information. So we're going to heavily utilize the fact that these two functions are inverses of each other to be able to understand the graph and important properties, because we went through in detail how to graph the exponential function. So remember, depending on the base, we have two different graphs. So we have one possibility of our base being bigger than 1, and then the second graph is dependent upon the base being between 0 and 1. So let's start with the first case. If we graph b to the x, we go through the point 0, 1, and the shape of our graph looks like this. So here is y equals b to the x. In the case our base is between 0 and 1, you still go through the point here at 0, 1, but your graph has the opposite shape. Okay? So here is y equals b to the x in this situation. For both of these, we hug the x-axis. When we then talk about its inverse functions, remember you're going to flip this over the line y equals x. And so all of your points are going to switch. So this point at 0, 1 is now going to go through 1, 0. Okay? And when I reflect this, my graph is going to look like this instead. So instead of hugging the x-axis, I now hug the y-axis. So this is our graph of y equals log base b of x for our base being bigger than 1. In the case our base is between 0 and 1, you're still going to go through this same point. So I flip the 0, 1 to now go through 1, 0. I still hug the x-axis, y-axis, but now my graph is going to go in the opposite direction. Okay. So again, just like when I'm graphing an exponential, I have one shape based on the base. Same idea holds for the logarithmic function. So what I want to do is I want to compare all the properties of the exponential to the log. Because remember, regardless of what our base was, we still had the same exact domain, range, y-intercept, x-intercept, horizontal asymptote, and vertical asymptote. So let's start with our exponential function. Its domain, remember, is all real numbers. We had no issues plugging anything into the exponential. However, the range was 0 to infinity. You would never get a negative number, and you would never get 0. So when I go to find all of these important pieces for the logarithmic property, remember they flip-flop. So what was the domain now becomes the range for my logarithmic function. Okay. And what was the range for the exponential becomes the domain for the log. Right. This is the thing that is super important. So remember, if you try to evaluate ln of 0 or log of 0, you get an error. If you try to evaluate log of a negative number, you get an error. It's because the domain has to be from 0 to infinity. If I start doing transformations, that's going to switch around, but we cannot take log of a negative number or log of 0. So this is undefined, regardless of the base. And same thing, log base b of a negative number is undefined. This is super, 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 super important for us. Okay. For the other pieces of information, we're still going to utilize the same concept that these kind of switch roles. So we do have a y-intercept for our exponential function. If I plug in x equals 0, my y value is 1. However, we do not have an x-intercept. We do not touch the x-axis. So when I go to find this for my log function, these kind of flip-flop. They're not exactly the same, right? But we do not have a y-intercept for the log function. We do, however, have an x-intercept. Remember, x and y switch. So my x-intercept is going to be the 0.10. For our exponential function, we do have a horizontal asymptote. We hug the line y equals 0, which is the x-axis, but we have no vertical asymptote. And then again, these kind of flip-flop, but not quite. We have some changes to make. There is no longer a horizontal asymptote, but now we do have a vertical asymptote, and it's the line x equals 0, which is now the y-axis. Okay, so we're just going to do one example of actually graphing. The more important thing is finding the domain of these logarithmic functions. So anytime I'm working with a log, I need to make sure the inside is positive. So for both of these, I'm going to do both simultaneously, just what we need. We always need this inside expression to be greater than 0. And same thing here, I need 1 minus x squared to be greater than 0. So just like we were dealing with the even roots, you set the inside of the root to be greater than or equal to 0. We kind of do the same thing here, but it's strictly greater than 0. Okay. Now for the first one, it thankfully is not as difficult to solve. I want to find what x values work, so I just need to add x to the other side. And this tells us 5 is greater than x, or this is the same thing as saying x is less than 5 if I switch sides. So we'll put this in interval notation, but 5 is our key number. I cannot actually equal it, and I can take all values less than it. So the domain of this function in interval notation would be from negative infinity up to 5, not equaling 5. Okay. When I go to do this next one though, now I have an expression inside of here. So this is not as easy as solving for x. It's a quadratic inequality. So really what I need to do is I need to factor. You can rearrange this if you'd prefer, but you can go about factoring this. So my first things have to multiply to 1. That's a 1 and a 1. The second pieces have to multiply to negative x squared. So that means there's a minus x and a plus x. Okay. You can check that the outer and inner cancel, but this is the correct way to factor. So we have two important numbers, x equals 1 and negative 1. So unfortunately, we do have to do interval testing for this to see which intervals work. So I put 1 and negative 1 in order. We definitely cannot equal these endpoints though, because we have a strict inequality. We're trying to see is 1 minus x squared greater than 0. And so I have 3 intervals to test. So from our first interval, we could pick x equals negative 2. And if I plug that in, it would be 1 minus negative 2 squared. We want this to be greater than 0. That's really 1 minus 4 is greater than 0. And unfortunately, this one is not going to work. Moving on to interval 2, 0 falls in there. So let's plug that in. That gives us 1 minus 0 squared is greater than 0. 0 squared is 0. So this tells us 1 is greater than 0. So this one does work. That tells us everything in interval 2 is good. And then last but not least, moving on to interval 3, we can pick positive 2 from here. And that would give us 1 minus 2 squared is greater than 0, which is 1 minus 4 is greater than 0, and unfortunately, that one does not work. So really only interval 2 is the one that will make this inside greater than 0. So the domain for this function would be from -1 to +1. So let's just do one last example. We're going to go ahead and get more practice again with our transformations. So we want to graph this using transformations. And so our starting graph, we just have log, means it's log base 10. So we're going to begin with y equals log base 10 of x, right? So I'm going to kind of do this piece by piece, but log base 10 of x would go through this point here at 1, 0. And it would have this shape because my base is bigger than 1. And then we would be hugging the y-axis. So we're going to find all those key pieces of information afterwards. Okay. Now I technically have a bunch of transformations within here. So the very first transformation I care about is what are my horizontal shifts. So remember our order of operations, we go inside parentheses first. So our first transformation, we have +2. This means we're going to move this graph left 2. Okay. So all of my pieces have to move to the left 2. So negative, or this one would go from 1, 0 to 1, 2, right here at -1, 0. Our vertical asymptote would go from here to the left 2. So now we're going to hug x equals -2. And then we still have this same basic shape. Okay. All right, so let's get rid of this graph now because we no longer need this one. Now I'm concerned with doing any reflections. So we do have this minus sign. And this minus sign is not attached to the x. So that means we reflect over the x. Okay. When I reflect a vertical asymptote, it's not going to do a single thing. It's still going to be in exactly the same spot. So our vertical asymptote will still be here at -2. My point here at -1, 0, when I flip it over the x-axis, is still going to be right there at -1, 0. And then the only thing that really changes is our graph is going to go in the opposite direction. You don't have to be an expert grapher. Do your best. I'm still keeping track of this point here at -1, 0. And then last but not least, we have this -1. That's addition and subtraction at the end. That -1 tells us we go down 1. Okay. When I move the vertical asymptote down, it's still going to be in the same spot. Really, the only thing that changes is this point moves to -1, -1. And then the graph is still the same. It's just been shifted down 1. So this is our graph of negative log of x plus 2 minus 1. I'm going to utilize this, though, to find my domain range and my vertical asymptote. So my domain is going to be from -2 to infinity. Those are the x values I can take. And again, this really just comes from setting the inside x plus 2 to be greater than 0. We can take x greater than -2. Our range is all real numbers. And then our vertical asymptote got shifted to -2. That's really the value that causes 0 on the inside.